We'll take a look here in this video about histograms and ogives. So what a histogram is going to do for you guys is it's going to group nearby values and display frequencies within certain ranges. So we take a quick look. Here's one on national SAT scores, maybe for the 50 states. And what we can see is all of a sudden data has been grouped together. No longer do we have individual data points, kind of like we saw before with a dot plot or with a stem and leaf plot, but now we're grouping things together. So all of a sudden we can see in that very first bar, well, one of the states had an average between 1350 and 1400. We don't know what exactly that score was, but we do know there's one score there. We know that most states apparently scored somewhere between 1450 1500. But again, we don't know the exact scores in a histogram. We kind of quote unquote lose that data. But we can start to see, well, how often do certain ranges of scores occur? So if we're going to construct these, the first thing we want to do is determine bin size. And a great way to kind of start that off is take the range and divide by 5. And that's because we want a minimum of 5 bins. That gives our reader a good look. It separates the data enough to start to look at analyzing the shape and the spread and that kind of stuff. We get a better feel for it. I will say you probably want to try to keep your bins, the number of bins, probably somewhere between 5 and maybe about 8 or 9, because if you get too many bins, then all of a sudden your graph becomes overwhelming for a reader. Frequency table, just a quick frequency table a lot of times makes a big difference as you're sorting through your data, and then we'll draw the graph. So, for example, let's say we have this data on Wake County, 20 of the Wake County schools. In 2008, their average SAT scores. So the first thing, as we're going to kind of sort this data, the first thing that we'd actually probably want to do is get the range. So it looks like we go all the way from 1304 up to 1766, which would give us a range of about 462, I believe, if I'm doing my mental math right. And then if I take 462 and divide it by 5, I end up with 92.4. Well, that's going to be kind of an awkward bin size. So this is where common sense, right? Identify bin size that makes sense. Well, a number that's very close to 92.4 and will help readers kind of see it. Maybe for this data, we do bin size of 100. Here we go with our frequency table. And now it's just a matter of going back and getting the count. So count 1300 to 1400. So we had 1, 2, 3, 4 scores, right? So we'd put a 4 here, and then so on. And I believe, keep going back and forth between looking at so there's a 1400, there's a 1400, so there are 2 of those. And as we pick through our data, what we should realize is there were 6 in the 1500s, 7 in the 1600s, and 1 in the 1700s. And so to create our histogram, it's just now going to be a matter of, well, let's give it a good title. Let's call it SAT scores. We'll get real creative. And then count or frequency, that will always be your x-axis. And I think the highest we went 3, 4, 5, 6, 7. And then our bins started at 1300. We went up to 1799, which means in terms of the tick marks on the bottom, we'll go all the way up to 1800. I need one more here. And so now let's just go back and draw the appropriate height. So we had 4 in the 1300s, 2 in the 1400s, 6 in the 1600s, 7 in the 1700s, and 1 in the 1800s. Now notice the bars touch. Bars touch. This is a big difference between a histogram and a bar graph. Because this is quantitative data, think about this bar, right? That first bar represents everything from 1300 to 1399. And then the very next group picks up right at 1400, so we don't leave any space between the bars. So we want to make sure that the bars are touching in a bar graph. All right. A different way of drawing that graph, right? It's the same data, but a different way of looking at it. Sometimes they might give you the center value in the bin. Notice that they've centered that up right in the middle of the bar. this is really just a matter of personal preference. I kind of like putting my bin where the bin starts at the beginning of the bar. To me, that's just easier to read, but some people might prefer to center those values up. And so if you want to center your tick marks, you need the center value out of the bin. It causes the reader to have to think a little bit more, right? To realize it's still bin size of 100, but you'd have to come down here to realize, okay, well, that's everything between 1300 and 1400. So it requires your reader to think a little bit more. But again, personal preference on that. So we've got kind of a bimodal graph here, right? If we wanted to analyze this distribution, we got kind of a bimodal, maybe a slight skew to the left. We could actually, since there are 20 observations, we could go through here and we could figure out where the median is approximately. We wouldn't know the exact median, but when there's 4 pieces of data here, 2 pieces of data here, and 6 here, the median is going to be somewhere around the 10th value. So we know that the center of the data is somewhere between 1500 and 1599. And again, just looking at the histogram, we know the range is from about 1300 up to 1800. All right. Now, sometimes they might just give you a frequency table. And so we could actually use our TI-84 or 83, your graphing calculator, and start to come up with an actual histogram using a frequency table. So the trick here, what I've done, right? So here's the original data. They gave you the bins already, and then the frequency within each bin. Now, notice we don't know the exact scores this time, right? But they've already been separated into their bins. So what we'll do is we'll do list 1 and list 2 in the calculator. And so once we have it there, we go to create our scatter plot. All right, we're going to turn the graph on and then make sure we select histogram. Now this time, up until now, this frequency list that is currently selected, we haven't messed with. But all of a sudden, we've got the frequencies of our score distribution sitting there, and that's in list 2. So if you hit second L2, now we go in here, we can do zoom. We'll go down to the 9th one, right, down to zoom stat. Nope, too far. Hit enter. Got our graph. Now, one thing that I'll take issue with, this graph makes it seem like all of a sudden there are gaps in the data, but we know how to fix that by just changing our window. Our X scale, we actually used a bin size of 50. So now if we go back in and graph it, now that looks more appropriate with our data. We see, okay, there's a skew left, unimodal. If we wanted to actually go in here and kind of get a better calculation for the mean and the median, there's a way we could do that. If we go to stat, go over to calculate, one of our stats, and here again, our data is in list 1, and then the frequencies are in list 2. If you've got the TI-83 or an old 84, you have to do one var stats and do L1 comma L2. Again, now all of a sudden we can come up with, it looks like the mean is somewhere in the low 1400s. We can scroll down and find the median is somewhere in the mid 1400s. So there's a way we can use a frequency list in the calculator. Now the other type of graph that we talked about was an ogive, and what that does is basically going to give us percentiles, a relative standing. If our data is normal, we can do a lot of stuff with percentiles by using normal CDF. But what if all of a sudden we have a data set like we just saw, right? That previous data set on SAT scores wasn't normal. It was skewed to the left. So an ogive is another way that we can start to pull percentiles. So to construct these, we want to consider what's our relative frequency, which is just a big fancy way of saying the proportion of observations. And we'll see how all this plays out in just a second. Cumulative frequency, well, when things accumulate, you add them up. So you are summing things up as you go through your list. And then relative cumulative frequency, well, that's just basically you're adding up the proportions. So here we'll use the data that we used before on just the 20 schools in Wake County. So there were 4 schools in this range, 2 schools here, 6 schools in the 1500s, 7 schools, and so forth. So relative frequency, again, it's just saying out of the total of 20 schools, 4 out of 20 or 20%, we're in this range, 10% we're in this range, and we're switching to percentages or proportions because we're looking to go get percentiles. Now, if we do cumulative frequency, we're just adding them up as we go. So here, there are 4. By the time we get to the second row, there's this 4 plus this 2. So now there's 6 observations. By the time we get to this bin right here, we've got a 4, a 2, and a 6 for a grand total of 12. We add another 7 by the time we get to the 4th row down. That's 19, and then 20 that are here. So now we just do the relative cumulative frequency. In other words, what percentage of the data is below where we are? So we started with 20% of the data. By the time we get to the second row, we have this 20% and this 10% for a total of 30%. So we're just accumulating the percentage. And we start thinking, all right, what percentage of the data is below this value? So we have 20%, 10%, and 30%. So that's 60%. Now you start thinking about what value is below. That's really what you're looking at here. A percentile is what percentage is below. So really, the relative cumulative frequency, big way of saying percentile. Right? 95% of the data is accounted for by the time we get to 1600 to 1699. And then finally, we have that 0.05. It adds all the way up to 1. So what we're going to end up doing with an ogive is we're going to graph the scores versus the relative cumulative frequency, or scores versus percentile. So to create this ogive, the first thing to think about, what percentage of the data is below a certain value? 100% of the data is below what value? Then we're going to use the relative cumulative frequencies in order. And the big question to continually ask yourself is, what percentage is below the value? So we go back here. What 0% of the data is below 1300? That gives us a starting point. All right. So I think 1, 2, there. We'll put our percentiles on this side here. And then nothing is below 1300, so that's our starting point. All right, so here's our scores. And here's our RCF. You could also just put percentile here. Now the question, 100% of the data is below what value? Well, everything's below 1799, but to make this a little bit easier for us, our graph doesn't look strange. We'll go to 1800. So all of the data is below 1800. So the last place we'll stop is 1800. And that puts us at, right, 1.0 or 100% of the data. 1800. Now it's just a matter, use the RCFs in order. So we start with 0.2. So think about it. Oh, where'd my eyes go? For some reason it's tracing back over. I apologize for how crazy this looks. All right, so then it went to 0.2. You think about it, 20% of the data was below 1400. Right? 20% of the data was below this value, not including 1400, but below it. And then it goes, this is going to be really frustrating if this is going to keep doing this. 1400, 1500. I'll just stop going back. You can look at your data there. Okay, so 100% was there. So we went to 0.2, and then it jumped up to 0.3. Then it was 0.6 in your chart, and then it was 0.95 in your chart, and finally to 1. Now just go back and connect the dots. Let me go put my title here, SAT scores. And what we're going to be able to do with this now, right? And you think, again, what percentage of the data was below a 1500? Well, that was 30% of the data. So reading this is really more important. So let's say that you are given an ogive. We want to say, all right, what's the 60th percentile score? So what you would do, go over from 0.6, go down, and that's the score of about 1590. We go the other way. What percentage of test takers scored below a 1700? So we'd start at 1700, go up, go over, and maybe about 90%. Let's say Gibbons was at 1631. What percentile would Cardinal Gibbons High School be at? So you'd go to 1631. We go up, head on over, and that looks like we're at about the 70th percentile. All right. So in the end, histograms and ogives, really good ways to display quantitative data. And it's really good to especially if there's a lot of data with histograms, right? Histograms allow us to show a lot more data very, very quickly. I will warn you, you got to be very careful with bins. Your bin size cannot change, but if you are looking at graphs, sometimes people will mess with the bins, or like all of a sudden a bin will be 100 observations, and then all of a sudden the bin size will shift to 50 or 20 or 30, just to try to make a graph say something that maybe it didn't say before. So be careful as you read your graphs, that you're paying attention to the axes, that you're paying attention to how these things are set up, because people will try to tell different stories, and they'll just mess with the axes and the bin size and whatnot to do that. And then just keep it in mind that ogives, again, really good way to show your percentiles.